Today, I'm gonna discuss with you why large earthquakes are rarely overdue on rift and non-rift faults globally. And when I use the term overdue, I have in mind scenarios where the elapsed time since fault last ruptured due to a large magnitude earthquake, it's less than its mean recurrence interval. So let's get started. It is well established that faults which are late in their seismic cycle are more likely to produce large magnitude earthquakes in the near future than faults which are early in their seismic cycle. This is why seismic hazard modelers calculate the likelihood of future events by comparing for each fault the elapsed time since it last ruptured over its mean duration, mean seismic cycle duration, with one full seismic cycle being defined as the time period between two successive large magnitude earthquakes on an individual fault. And long paleoearthquake reports, such as the one you see here in this schematic trend slope, which is, by the way, from a normal fault, provide a unique opportunity to quantify both of these parameters, the time since the last event and the mean recurrence interval on a specific fault. So in this notional trends log, we have identified 6 paleoearthquakes, with the most recent being a historical event. Now, the recurrence, the elapsed time of this event represents an open recurrence interval, while the time period between the preceding paleoearthquakes represent fully closed recurrence intervals. Now, the elapsed time since a large magnitude earthquake occurred on a fault over its mean recurrence interval can be used as a measure of earthquake cycle maturity. We name it here normalized elapsed time, and for brevity I may call it net. And we see that we consider that for normalized elapsed time values less than 1, the faults may be considered premature or early in the seismic cycle, while for net values on individual faults greater than 1, this fault may be considered overdue. So the fault that you see schematically here on the left, which is a normal fault, okay, for the time period on this graph that plots above the red dashed line, which represents its mean recurrence interval, this fault is considered overdue. Now, in the remaining few minutes, I will try to address 3 key questions. Which are the factors that control the observed relationships between elapsed time on a given fault and mean recurrence interval? Why there are so few faults globally which are overdue? When we started this analysis, we were intuitively expecting to find, a balance between faults which are late in the seismic cycle and faults which are early. Nevertheless, we came across faults which are mostly early in the seismic cycle, and here we ask the question, why is that? And also, since we are talking about, we're more interested here about normal faults and rifts, we want to see whether there is any difference between different fault types. And finally, we would like to discuss whether existing historical information from historic ruptures can be used to improve estimates of time-dependent seismic hazard models. So to address these questions, we put together a large data set of paleoearthquakes and faults from around the world. Here on the left, you see the 5 regions that we have sampled. In total, we have about 900 paleoearthquakes, which represents the best data available, I believe, on the globe currently. These paleoearthquakes were produced over a period of about 50,000 years due to earthquakes on more than 200 faults. As you see here, our data set includes a wide range of fault lengths, slip rate values, mean recurrence intervals, because our tectonic regions include very diverse structures, such as plate boundary faults, very fast-moving rifts, such as the Corinth and the Taupo rifts in Greece and New Zealand, respectively, moderately to fast-moving forward settings, and very slow-moving intracontinental extensional basins, such as the Basin and Range in the US and the Taranaki Rift in New Zealand. I would like to share with you the 2 end-member examples for our data set. On one hand, we have Japan, where we sampled all fault types, strike slip, normal, and reverse. And we have a nice mixture of paleoearthquake faults with red and without, with blue historical ruptures. And on the other end of the spectrum, we have Greece, where most of the faults sampled here are normal faults, which ruptured historically, are red, as you see, and they were subsequently trenched. Nevertheless, because we have a large data set, this decreases any potential biases introduced in our results from our sample population. And to test this, how representative are the faults that we sampled here, we have plotted on these 2 graphs each fault, color-coded as per fault type. You see down here. So we have plotted the slip rate on each fault as a function of its fault length for each fault, and mean recurrence interval. And you see that in all cases, but also for the individual fault types, we have positive and inverse or negative relationships between these parameters in agreement with well-established international fault scaling laws. So that gives us confidence that the sampled fault population is representative and suitable for the subsequent analysis. So here I want to share with you the results of our analysis. On the I should say that each graph here represents a study area. Each circle in each graph represents a fault, for which we have compared on the y-axis the elapsed time since this fault ruptured last over its mean recurrence interval, calculated from the paleoearthquake records. For the purposes of our seminar, I want to point out that these 2 regions are dominated by normal faults, are nearly exclusively extensional. The data here are extensional. And what we did, we divided each graph in 2 parts, below and above the 1-to-1 line. And we see it's pretty clear, I believe, that the vast majority, about 80% of the sample population in each region, but also collectively, plots below the one-to-one line, indicating that most of the faults that at least we sampled here are early in the seismic cycle, which is, as I said, a result that it was somewhat surprising. Now, because about 1/3 of this population, the faults which are highlighted here with a black outline, if you can see, derived from historical earthquakes, we were wondering whether this is introducing a bias in our results. And for these historical ruptures, we calculated, instead of elapsed time since the last earthquake, which is obviously quite close to the present, the time period between the historical rupture and the penultimate event. And we superimposed these results on the same graphs. And what we see is quite amazing. We see that most of the data points straddle the one-to-one line for the same faults, okay? And they plot mostly prior, but very close to the mean recurrence interval, indicating that most historical earthquakes occurred near the end of the seismic cycle. An exception to that is California, where about half of the faults, 50% approximately of the population, plots above the line. So I should say that the mean normalized elapsed time for the entire population is 0.9, approaching the unit, which is, as I said, pretty impressive. Two of these regions are represented by normal faults, so we don't see a significant difference between rifts or extensional setting and other regions that include various fault types. These are the same data plotted together on single graphs for the open interval paleoseismic data and for the historical data. The scatter associated with the open interval paleoseismic times and the tide population produced by the closed intervals are very clearly illustrated in these graphs. Interestingly, if we look a bit closer on the closed interval data, we see that the lower end of this tide population is dominated by the Californian faults, whereas the other end, the upper end, is dominated by the black triangle and other faults, but the black triangle are exclusively plotted at the upper end of the population, which is the basin and range faults. This finding implies a dependency on strain rates, and we wanted to test for that. And this is what we do in the lower graph here, where we have plotted the percentage for the open interval paleoseismic data, the percentage of faults which are overdue, okay, in each region as a function of slip rate. And what we see is that there is indeed a dependency with faster moving faults or fault systems having more faults in the overdue fields than slow moving faults or fault systems. Predominance of premature faults in our global dataset may be due to the fact that we sample mostly low slip rate faults, which is what we find globally. Now, to explore a bit further the underlying causes between elapsed time and mean recurrence interval, we have plotted here for each region we have tried to test which recurrence model describes the closed interval data, which are the best behaved, if you remember, with the red data points. So we wanted to see which of the known distributions best describes these data sets individually, but also for the global. Okay, the data themselves are represented by this wiggly black line in each graph, and you see is indicated here with the red letters that the best fit in nearly all cases, but also for the global population, it's there are two distributions: the viable and the log normal, which are both positively skewed distributions. So it is possible that there are so few faults globally which are overdue because the recurrence interval is characterized by positively skewed distributions where the mode and the median is less than the mean. The next step, the last I'm going to talk about today, is that we took the best fit distribution for the closed interval.
Vasiliki, you're now past 10 minutes.
Yes, thank you. So we, as a last step, we took the best fitted distribution for the closed data set, and we said we wondered whether we can reproduce stochastically the open interval paleoseismic data. Okay, and these are the results for each region separately. We see that the stochastic models, which are represented by the gray shading in each graph, reproduced quite well, 70 to 80%, the open interval paleoseismic data, which are represented by the color-coded lines in each case, apart from California. Okay, you can see this more schematically here in the last panel, where we have histograms indicating the degree of overlap between the simulated, the gray, and the open interval paleoseismic data, and you see a very good fit for all data sets apart from California, which is plotting out at the left and forms an outlier. So from this we have two main conclusions. One is that we are led by these findings to propose an alternative approach to defining open interval PDFs for seismic hazard modeling instead of using the traditional approach that involves the elapsed time since the last event. Here we propose to use the closed interval between the historical ruptures and the penultimate events. Okay, the other methods I would like to point out is that although Californian faults are among the best studied faults globally, and they're really detailed and very well constrained paleoearthquake series, very long paleoearthquake series. Unfortunately, it seems from this analysis that the faults in California are not representative of the faults globally, and because many seismic hazard modelers are tuning their models to the Californian recurrence models, this may introduce a bias in other regions around the globe. So to summarize, what we did, we analyzed the best available paleoearthquake data as to date. We analyzed them in terms of elapsed time and mean recurrence interval. We found that most faults are early in the seismic cycle. We attributed that to faults that follow recurrence distributions which are positively skewed, together with sampling low slip rate faults. We didn't find any significant difference between rift and non-rift faults. That's clear. And yes, in general, we found that despite the very diverse tectonic settings sampled here, that all faults behaved approximately similarly, apart from California. And last but not least, we are proposing an alternative approach for perhaps improved estimates of time-dependent seismic hazard models that involves the historical rupture and the penultimate event, as opposed to using the elapsed time since the last large earthquake. Thank you very much for your attention.
Awesome. Thank you very much, Vasiliki. Do we have any questions for Vasiliki? To get started, I have a quick one, and I know Kim also has a quick one. So you did mention that you think that the database was dominated by bias sampling towards low slip rate faults globally, aside from excluding California, right?
Yes.
But you also did mention that you also use the term immature faults to describe those faults. And I was wondering if one could equate low slip rate faults to be representative of the seismic cycle of immature fault, like faults that are shorter length, if you get what I mean by immature, shorter length faults that do not have as much mature structural characteristics as mature.
Perhaps I was. Can you hear me?
Yes, yes.
Yeah, no, I didn't mean the immature in the sense of maybe perhaps as you mean it in terms of duration of existence of the fault.
Okay, I see.
It was more mature or immature with respect to a full seismic cycle.
I see.
So when I say faults are early in the seismic cycle or late, I mean this is with respect to when a fault ruptured last.
Okay, thank you.
So,
Makes sense.
Yeah.
All right, Kim, you go, and I see some hands coming up.
I was just curious, how does this translate into the seismic hazard maps? Are these findings likely to reduce hazard ratings for certain places, or does it just mess with the time scale over which that hazard is expected to be present?
Yeah, thank you for your question. What we propose, normally, the number of faults globally that we know when they last ruptured, it's a very small number. Okay, it's a very small number. So for most faults, what seismic hazard modelers are doing is they're setting the elapsed time because they need to know when the fault ruptured last. So they set the elapsed time to the length of the historical seismic record. So in New Zealand, it's 200 years. In the US, it's 350 or 400 years. In Greece, it's a bit longer. But this is an arbitrary number. What we say here is instead of doing that, we found that the global population of closed intervals from the historic ruptures and the penultimate actually reproduce very nicely the open interval paleoseismic data. And instead of doing that, we could draw from this population to try to estimate time-dependent seismic hazard. So we're neither, saying that we will reduce or increase the seismic hazard. We just propose an alternative approach that we see it has worked well, at least in this sampled data set.
Very cool. Thank you very much.
All right. We have two more questions. Two more people raising their hand. Constanza Rodriguez, do you want to go?
Yes, thank you. Thank you for the very nice talk. I was wondering because in your analysis you use the mean recurrence time, but this would better characterize the fault behavior if the recurrence was periodic. But some faults, we know they might not behave in a periodic way. So I was wondering if you use any other metric to characterize maybe the medium or so on.
Okay, I'm sharing again my screen. Is it visible?
Yeah.
Okay. Thank you for your question. It's a good one. I should have mentioned here that the notional earthquakes on this trench log occurred in a non-periodic manner. I was hoping that I would speak last, so the speaker before me, I assume she would have introduced some short-term variability, and this is exactly what is shown here by this blue line. So I should have mentioned that we only kept long paleoearthquake records, when I say long, with 4 or more earthquakes, hoping to overcome the short-term variability and derive a reliable and robust mean slip rate. Therefore, a reliable and robust mean recurrence interval. Okay, so we really need to use and to pick the best available paleoseismic data. And this is not easy because there are not many faults with long records.
All right.
Okay, thank you.
Thank you. Okay, we're going to take the last question quickly so we can get to the next speaker. Scott, please go ahead.
Hey, thank you very much for the talk. That was really interesting to see from as a paleoseismologist from Western North America to see this data kind of represented in a great way. And I'll never forget the late David Jackson reiterating and stomping his feet talking about this California problem, right? And so I'm trying to imagine, if we go back, if we were all paleoseismologists 300 years ago, would we have seen this California problem? And I think what you're showing us is that we probably would not have, because it's just the current open interval that's the problem, and the past recurrent blocks of time would not have stood out as an anomaly. Is that true? And would you have come to the same conclusion that when you said fast slipping faults can be more problematic, right, and stand out like California? Would you have come to that same conclusion if we were paleoseismologists 300 years ago? And if not, why?
That's a very, very good question. And thank you. I was hoping that someone will comment on the California anomaly. So, yes, it's true. The Californian faults appear to be overdue more than the other data sets because as other colleagues from the US have pointed out that there is a hiatus in earthquake occurrence right now. And I would say, yes, if we were 300 years ago, or if this work was to be done 100 years later, that most likely, some earthquakes would have occurred. Californian faults would fall back to like an average behavior if they would sit together with the other data sets. So if there's an earthquake or earthquake cluster, within the next, I don't wish that, but within the next 10 or 20 years, yes, California faults will plot perfectly in alignment with the other data sets. And we see this for the penultimate event. The time period between the historic and the elapsed, they don't show any difference to New Zealand faults or Japan, etc. So yes, thank you. That's a good question.